Right. As I made an announcement 2 weeks ago, maybe, or last week. So we're not going to meet next Wednesday. Around this time, I think I am on my way to Boston still. So I'm going to record my lecture on weekend and post it so that you can watch it. The module that we are going to cover the next week is hands-on. So what you need to do is that you need to the hands-on video, you cannot simply turn it on and let it go, then you don't get any. You have to pause at some points and practice it and make sure that your program runs the way that I give it a demo. Okay, so you have to pause multiple times, or sometimes you may need to repeat. Okay, rewind, tape, rewind. It's not really tape, right? So you have to repeat watching videotape, video clips if you cannot follow my hands-on lab. Don't expect that you can follow my hands-on lab at the same pace as I give it to you. Okay? Don't expect that much. I may give you about hour lab, which may cost you maybe 3 hours, 4 hours, who knows, maybe 1 full day or 2 days to catch up. But you need to make sure that you follow. Okay? That is classification. So I'm going to give you the concept today, and I'm going to, JP, welcome. So Tapanzi is okay for you, right?
Yeah, no, it wasn't that much traffic. I hear the other side's completely bad.
Yeah, I heard some news from James. I think there is a mapping issue. GPS runs well, but your map is not really updated, so still 287 Tapanzi, old Tapanzi appears on your map, and then it's right, and some annotation. I think it should go eventually, right?
Yeah.
That old ones.
Morning traffic is horrible.
Is it worse than
It's worse.
before? How many lanes open at one side?
4 on both.
So we usually have 4 lanes each, right?
Well, it used to be 3, 4.
3, 4, yeah, vice versa, right. But 4 each, then 8 lanes open right now.
It should be better, but there's more cars merging in from exits near the bridge, and they made the exits really short, and everybody has to.
So what happens is that if both lanes are completely done, then it's total 16 lane bridges.
Yeah.
Wow, it's quite wide.
They're using 2. I mean, one's gonna be like a sidewalk for pedestrians, and one's gonna be for emergency vehicles only.
Oh, is that right?
Yeah, and then one's gonna be for buses only.
So we can walk now, which means one day last Friday I took George Washington Bridge from New York side to New Jersey. Police car is in the middle, and then police officers standing. I think about 5 police officers standing and then looking down, and then 2 helicopters is searching through the Hudson River. So somebody
somebody. You're making it easier for people to jump now. On the Japanese bridge.
Japan is a fence is low, yeah?
No.
I think they probably make it higher, right?
They're making it higher.
Right. Here also, Asley overpass fence is pretty higher.
Yeah.
So previously, very easy to jump in the under passing cars. It is really dangerous. Not only that, I think about 20 or 30 years ago in Washington D.C., there's a loop. We call that Beltway. One high school girl, I think maybe middle school girls, throw the pebbles and stones, but she threw small pebbles to the Beltway, but the speed, the Beltway is about 6 miles, at the lowest 60 miles, right? 70 miles. So cars runs 70 miles, and then stone drops, a lot of casualties. So they make a big fence after that, so they cannot throw.
I mean, they said that they were also going to put like netting underneath the bridge, just in case someone does somehow climb over the fence.
That is also
That
right.
They won't be able to do anything. They'll be trapped down there.
Right.
That's what that's like.
Sheikh, welcome. All right. So next week, you and I meet virtually, not physically here. Okay. So the topic that we are going to cover today is classification. I'm going to change this. We are not going to use that one, but only all. What did I say here? Oops. Previously? I said here SCI kit dash learn, right? This is another package for machine learning. SCI kit means a scientific kit for learning, for machine learning. That package is written in primarily Python. So sometimes I teach Python programs, but in this semester I'm going to stick to R script only for some reason. Not only, I mean, occasionally we will do a little bit of Python, but R. Yeah, if there are two avenues available, one avenue for Python avenue and R avenue, then we will go for R avenue. Okay. So in this case, that is for R. What we will do is we're going to learn a decision tree. Use it and construct it and use it. I am going to give you the construction issue, and using is very, very simple. Once a decision tree is made or provided, then you just follow some condition statements and go to the path that it guides you. So that is simple. So whatever the node that you reach, that is the decision that you can take. So using decision tree is very, very simple. Construction, some issue. But if you construct using a tool that I am that we are using, it doesn't construct the way that we expect, because it has its own construction strategies. Okay, so you would see that. And another concept that we are going to learn for classification is K nearest neighbor. K nearest neighbor. You can think of your neighborhood. And probably you closer. You have a closer neighbor, closest neighbor next to your home, right? Usually, but not necessarily. Sometimes your closest neighbor may be the strongest enemy. But anyway, nearest neighbor. K nearest neighbor. The idea is simple. In your town, you have basically, let's say, it's not really realistic, but let's assume in your town there are two kinds of neighbors. Your good neighbor and bad neighbor. Good neighbor and bad neighbor. Somebody moved in your town. Then you can classify that new movers either good neighbor or bad neighbor. How do you decide that newcomers are good neighbor or bad neighbor? How do you, Jess?
I guess certain factors, like if they're loud, or if they make a mess, like in the street.
Or dump their brushes into your home there's a season, right? They blow the brushes into your backyard or front yard in order to clean their front yard or backyard. They don't care others, but they do care their front yard and backyard. But anyway, so somehow you have characteristics of a good neighbor and bad neighbor, right? Good neighbor and bad neighbor. So when you look at newcomers, then you need to try to find out what kind of characteristics that new movers possess. Does that family have good neighbor characteristics or bad neighbor characteristics, right? So you try to find out some similarity. How that new family is similar to good neighbor or bad neighbor. If that family are more closer to bad family, then you can say that family may be 60% bad family and 40% good neighbor, something like that, right? So that is exactly that we can describe here. Okay. So in order to do that, we need to have distance function. Okay, distance function. Distance function is very similar to the distance measurement in your algebra. Okay, if you have 2 points in 2-dimensional space, right? So how do you measure distance between 2 points? Let's say here you have x1, x coordinate, and y1 for y coordinate. Here also x2 and y2. So you have one dimension, say this is x, and another dimension that is y. You can say this x axis is for like dump habit. How many times this guy is a dump to a neighbor or on the street in between, right? Number of dumps. And another ones maybe, what are the characteristics for good neighbor and bad neighbor? Noisy, right? Bad neighbor, I mean, to me, maybe not to everybody. I don't like the party neighbors, so they party all weekends. From Friday, they turn the volume up and then loud music until midnight at night, and Saturday also, and Sunday also. Then I treat that bad neighbor characteristics. Maybe it depends on, right? Somebody wants to listen. If your neighbor turn on loud music, and you may have some good side effects, so that you can dance at your home according to the music that you can listen. But anyway, some noise, right? So in this space, I can draw only 2-3 characteristics. We call that feature, right? Feature. Well, 3 features if you use 3-dimensional. So one more axis here. But in this case, we use a 2-dimensional space, and the distance between two of these is simply x1 minus x2, and we square it, and plus y1 minus y2, and then we can power, and then we use square root. Okay, so this is a distance. We call this Euclidean distance, right? Euclidean distance. There are Euclidean distance is one specific distance, and therefore this notation, a formula, can be generalized. Okay, and also we can reduce this to another level, that is Manhattan distance. Then we can call simply in the Manhattan distance, where's my paint? Okay, Manhattan distance, you've heard of that from some Manhattan. See, if you think of Manhattan, then all the streets are in grid shape. You cannot pass from, let's say this is one block, then you cannot walk from, for example, southeast to northwest. You cannot walk directly, right? Because this is a building. In order to walk from southwest of the block to the northwest of the other side of the block, then you have to walk up one side and then cross another side, right? So that is the distance. We call that a Manhattan distance. So that is a more specific, specialized distance from Euclidean. That can be done in this way: x1 minus x2, x1 minus x2, absolute value plus y1 minus y2. And again, there is absolute value. We call that Manhattan distance, NP distance. Okay, this is Euclidean distance. So we're going to use this. Another technique that we are going to use is SVM. What is SVM? M for machine. This for machine. V is vector, so vector machine. So there is some vector expression. And as for support, vector machine. So we're going to learn the concept of support vector machine. All of this, we're going to learn the concept, and then rather than programming, we will learn not the application packages, but tool. Okay, so a little bit of somebody say coding, but you may say scripting. It's not real programming language, but it is a little more detailed than SQL expression. But this is a lot simpler than programming expression, programming language expression. It's not like Python. It is not like Java or C. It's a lot simpler than that. But it's not as simple as database, simple database language, okay, like SQL. Okay, so why classification is needed? First of all, classification is one of the major topic in machine learning. Then somebody may say, why machine learning is important in cyber security? Then I would say, number one, not all the intrusion detection and prevention can be predefined. The major cause and damage may come from the first attack. Okay, if you do not know the things, for example, ransomware. If you have a ransomware, this my laptop has 2 times of a ransomware, but it is a fake ransomware, not real ransomware. Like this afternoon also, I had that. When I turn on some web pages, they sent me some fake ransomware, so I immediately shut it off, and I detach all my file system is external, so I'm not going to use my file system on this laptop or my other machines. I'm using always this. Okay. If this has some attack or malicious program running, then this is possible also, but not directly, not at once, right? That attack my internal hard drive first, and then that program may see external drive through USB or whatever the port. But right now, that is the reason I'm keeping all of my materials externally, right? So if my laptop is stolen, as far as I have external drive with me, I am okay, right? I am okay immediately. So not all are predefined, and once it is attacked, then damage is paramount. From the second attack, hopefully there may be some antivirus released so that you can use it, and from the second time, your program may be protected. But only the problem is the first attack, right? That happens always. First attack is a big problem. There is no exercise. Same thing in military, right? Fabio? Military, if you are attacked once, that's it. War is over. You have to win from day one. Okay? So when I was military, our slogan, our catch is this: if you don't kill him, you will be killed. Kill him or be killed. Oh, we have a JP also. So have you killed anybody? Not directly, right? Unknowingly. Who knows, right? Unknowingly. Well, anyway, so your program needs to be adaptive to any attack, not just the way that you predefined, but if you can, and therefore if your program becomes a little bit intelligent, so that knowing pattern X, your program understand pattern X2, knowing X1, and also expect or predict X2, then that is great, right? So that is your future the software or applications that you expect or you develop. Another reason is that because of that first reason, nowadays attack program is also developed using machine learning technique. Attack program is not just a simple program, but attack program also evolves by itself. If one-time attack is invalid, then second attack is not the same, but tweaked a little bit by itself and try to attack. So your defense program may defend once, but may not be defensive to the evolving attack programs, right? So attack program and defense program give effect each other so that they improves both ways. Network. If you think of the attack on your computing infrastructure, the first thing that you can think is a network packets, right? If you can identify network packets very quickly, then you may be able to protect your systems. So a lot of companies now trying to put their efforts on analyzing packets as quick as possible on the streamline and at real time to find out any element, any malicious element there. Once we know, then how can we so your program somehow needs to train by itself. Okay. In learning, there are basically two types of learning available: supervised and unsupervised learning. In conclusion, classification is supervised learning, whereas clustering is unsupervised learning. The difference between those two is the existence of a teacher. If there is a teacher to train, okay, then that is a supervised learning. If there is no train, because there is no training data, and real testing data is not just in the similar format of training data sets, then that is unsupervised learning. So the concepts and techniques, software packages that we could do for clustering assumes unsupervised learning. Therefore, there is no teacher. One of the very sophisticated algorithms is a genetic algorithm. You know, genetic. It's not generic, but genetic. Our human genome components are evolving, which is not according to the teacher's instruction, right? It evolves by itself, knowingly, unknowingly. So there is no teacher. We call that mutation, right? Some gene or some DNA may be changed, updated, modified abruptly. We call that mutation. Mutation occur non-zero possibility. Non-zero possibility. In other words, mutation is always possible. Not frequently possible, but it is not non-zero possibility. So always it may happen. The program is very, very interesting, right? It's like a father and mother. So we have two players. Okay. They share half of mother side, half of father side to make a one complete entity. We call that crossover. While we have a crossover, very rarely, but not impossible, to mutate one of many genes. So we need to expect that. Okay, that is basic idea of a genetic algorithm. We can program it, and that is unsupervised learning. So one of the well-known algorithm is genetic algorithm. Another algorithm is another technique is neural network. You've heard of that, right? Neural network. Both of those are called, in other words, deep learning. Deep learning. It is not shallow learning, but deep. The techniques in deep learning outperforms human capabilities if that technique applied to a specific application domain. A specific application domain. You know that, right? One of do you know the Chinese Go game? It's like a chess, but a lot more complicated. One movement, to take one movement, that one movement is chosen from usually 199 to the power of 199. What is it? How many? Unlimitedly many. So we choose one movement of chess. You can say chess, okay? So a lot of repetition and possible combinations needs to be taken into consideration. That type of things can be done a lot faster in computer than human. Human can do somehow in certain level, right? So world champion of that Go game, world champions, not only one, right? A couple of world champions, a couple of Korean players, a couple of Chinese players, all are defeated by computer, which is implemented in deep learning. Okay. Anyway, that is unsupervised learning. The idea is that that program learns, that program keep learning as it plays the game. The more that software plays with the human experts, the more intelligence that software will be having. That is the issue, right? That made so that idea is unsupervised learning. So today we will do a classification, which is supervised learning. So let's take a look at one more here. Supervised learning has a supervision. So training data sets are accompanied by labels indicating the class of observations. See, what is the teacher? Teacher says, hey, label. So each records, I want you to imagine a table or Excel spreadsheet. So each row of that Excel file contains all the features of that entity, that first objects. So at the end, somewhere, the teacher says, hey, this is a good guy. what the second layer, second row, teacher says, oh, this is a bad guy, this is a good guy, this is a good neighbor, this is a bad neighbor, and things like that. Okay. One of the examples that we are doing in next few slides, who can purchase a PC? So there is a database, maybe Best Buy store. They probably have some databases. If they collect some customers' information, then customer type. So maybe students or employees or employer or self-employment or whatever. Okay, housewife, whatever. Right. And then there's income, sustainable over income. And also age, right? Young students, if that student does not have money, cannot buy, right? But as far as young students who has money, definitely buy PC. That is our observation, right? So if our data explains that pattern, then your program learns from the data. And next time, when customer comes in, if a salesperson quickly access the customer's information and learn it, and therefore that program says, hey, this guy definitely purchased a PC today. Then what you need to do? Salesperson treat him very well, right? Does not need to enforce to sell, but ready to sell. So, with some observation with the labels. When it comes to new data, then quickly classify it so that this new data also can be labeled. Okay, that is a classification. That's what we are going to do today. So back to the network packet example, we want to classify the packets so that according to the labels, each packet, the teacher tells us that, hey, this is a good packet, good network packet. This is a bad network packet. This is a malicious packet. This is a good packet. This is our valid customers packet. And some types of labels are given. Okay, so your program learn something from that known data sets. We call that training data sets. That training data sets has already labeled, decision labeled. So according to that decision labeled, when it comes to new records, we also give decision label. As we looked at the training data sets. So every time we compare, we may compare with some distance function. Okay. Once we declare, once we classify, then we can also do some predict. And then there are two terminologies available. in computer science or artificial intelligence, we call it classification. In mathematics, there's a numerical prediction. So the difference between those two is that classification predicts categorical data labels, classifies data based on the training set and values in a classifying attributes and use it in classifying new data. Numeric predictions, it models continuous valued function, so more like based on function. So prediction is also based upon some function. So this is based on function, and classification based on data. Okay. Typical applications for classification or numeric prediction is a credit approval or loan approval. Loan approval is very, very simple according to that classification paradigm, right? Each bank, loan officers, has tons of records. Each record has a label saying that, oh, this kind of loan is a good loan, succeeded. Another kind of loan, eventually this type of loan may go default. Okay, so they have some good records. Okay, last couple of decades, they have records. So your program learns well-known records, and then when the new data comes, new application, new loan application comes in, then your program quickly understand that, hey, I saw similar case. So according to that similar case, this guy go bankrupt in next 5 years, for example. Therefore, decision is denied. That type of loan approval process already employed about 20 years ago. When I first learned artificial intelligence, the company's loan officers, loan decision is made by human only at that time. So each bank there is the loan officers, each branches. Nowadays, a loan officer is not stationed at one branch. Maybe one officer covers 10 branches or 20 branches. Whenever they have some, and then that officer is not really a high-paid officer. It's not like 30 years ago. Right? It's nothing but tellers in bank. Previously, there's really high-tech positions. Because everything can be done. What they do is they just key entry and ask user to submit some documents. And then loan officers simply enter according to the documents and then wait the response from the software packages. And in entire bank, there are a few we call that underwriter, right? Underwriters, the human is available. If there is some case applications in marginal, then human is involved. Other than that, 90% of applications can be determined by software packages. Loan approval, medical diagnosis. Oh, this is really comes very quickly, right? Human, see your internal medicine doctor. You go to internal medicine doctor, right? Usually, before you go to some specialist. That position is really will disappear sooner or later. Human diagnosis has some problems because there is based upon limited knowledge of human. If you rely that on software packages, then that software has all kinds. It's a lot more knowledge that human doctor can use at certain point in time. And then the examination, medical exams, will be more complete than the examination planned by human doctor. Human doctor, when I go to my doctor, then occasionally he took some blood, right, or urine from me, and the way that he checks, he requests for lab examination. It's based upon my explanation. If I says, "Oh, I feel something wrong," then he check. Okay, then we will examine this. Anything else? If I don't say nothing, then he can. Okay, then we will do diabetes test and cholesterol test. So some tests very common, right? And then check that common test, and then a couple of additionals in response to patient request. That's it, right? Not based upon my record or my condition. So, fraud detection. Oh, these days a lot of fraud, right? I had an experience from Uber. Last Christmas season, because I have my cousin visited from South Korea, so he stayed in the city. So I visited him in the city, and one time he said he has he needs to know Uber. Okay, I've never used Uber in my life until that time, but my cousin says back in South Korea there's no Uber, right? He says I want to see how Uber is operating. So I immediately downloaded Uber and then I called, okay, and we moved from one club to another club at that time, and we paid about $10, okay, and then I forgot, and then all of a sudden in this summer, okay, it was maybe in June, so it's about 5 or 6 months after I first time used it. First time and last time, only once I used it, and then my credit card keep charging the Uber. So I called my credit card companies. I've never used that, and then I always denied it. But it kept requesting for about 2 months. So I cannot do that, and I called my credit card companies. They said either you decline anything from Uber, that's what they do. So they will set up no request from Uber will be processed. So that lady set up that fraud. Fraud is detected by me, not by software, not their credit card companies, but detected me. But in order to prevent that credit card setup, some. And then I called Uber. Would you be able to verify that certain transactions? So I had about 20 transactions, all fraud. It's not really big money, $10, $11, $7, something like that. But end up it's over, I think, $150. So that request. And then finally, I removed from my cell phones, and I removed myself from the Uber accounts. And after that, it's all, it never happened so far. Okay? So that is a fraud, right? I do not know who keep requesting. But I still remember that driver on that night. The car was really good SUV, so comfortable. So I gave him a tip, extra tip. But I'm not sure it is requested by that driver, or that driver also the data compromised by someone else, right? But no one wants to investigate. Credit company do not want to, and Uber company do not want to. They don't want to do investigation. They just to refund. Okay. Uber driver may not know, right? That, right. Somebody, right? Somebody. If that comes from the same Uber driver, then that Uber company definitely knows, right?
More than $10 billion. More than $10 billion.
Then they will investigate.
Yeah.
So should I lose $10 million?
Yeah.
I don't have even point.
Really a mistake.
Okay.
After around like 4 or 5 years later, just say, yeah, really a mistake.
So I do not know finally who lost money. I don't lose money because I got all credit back. Is it a credit card company or Uber? Uber? Then Uber, somebody used the service, right? From Uber service. Maybe service or somebody withdraw cash. So Uber is losing. So Uber business is not going well now, right? I heard some news. I didn't pay attention, but Uber business is not is not increasing as usual, right?
They have competitions now.
Is it because of a competition or? Or is there some technical issue? They used to go very well, and therefore they invested a big money for Uber, autonomous Uber, right? They set up the lab in Carnegie Mellon University, and I heard in Pittsburgh there are quite a few autonomous Uber running. But when they call Uber, the driver sits, the passenger sits, and then driver sits, there's nobody, and The passengers sits back side. That's that they now run in Pittsburgh City. So I heard that. Right. So just in case if something happens, then that human driver currently sitting at the passenger side involved to treat. But anyway, they said it's almost 100% accurate. So technology has no defect so far, but fraud is not from technology but from human.
What does mean?
Human. There's a lot of bad humans. So we need to have some classification software so that software, whenever software sees human, then software quickly decide, hey, this is good guy, this is bad guy, this is good guy, bad guy. For a specific target, right? Specific target. So for bankers, if a customer comes in, they quickly, oh, this is a good customer. This is maybe theft. Yeah, airport entrance. That software, airport entrance is more likely, highly likely use that type of systems, right? Because the passenger information is already there. So that software can classify passengers. Good passenger go through quick, fast lane. Bad passenger then double search or triple search. That may be possible, right? Web page categorizing. Web page is also, right? When we set up web pages, then I'm not sure. Yeah, not quite sure. But that is a potential applications. All right, classification, 2 steps process: model construction and model usage. So model construction, there. If we have a training data sets, so we trained the software. So software has some model to be constructed, and the next phase is a test or practice. That is model usages. So example here. If you have this is a very simple table, right? Faculty tables. So Mike, Mary, Bill, Jim, Dave, and there is a rank: assistants, professor, associates, and year, number of years, and then status of a tenureship. So tenured or not tenured yet. So that is a real data. Let's say this is a real data. This is from the textbook. Remember that we have textbook. This is real. From this real data, so there's some patterns learned. Okay, so we call that classifier. So classifier is built. Okay, classifier is built. So one of the patterns that classifier has built is this kind of a rule. If rank is professor or number of years greater than 6, then tenured. That kind of a rule learned from this. Okay, this is a knowledge discover. But data mining itself do not need to construct a rule like that. Okay, this is a rule. do we really need a rule? If we have a rule, then we apply this rule to new data which comes in. There's a rule processing. But data mining is not necessarily rule processing. Data mining itself is that looking at this table, if we have another record, okay, that record's a name, say Jill, and rank, associate, and years, I don't know, maybe 5 years, and then this is a target that we want to learn. Okay? Then what happens here is that our training set says this kind of records is a positive record, and the rest is a negative records. Positive, negative, based upon the targets that we are looking for. The target value that we are looking for is that whether that record has a tenureship or not. So this is a target. So our sample training data sets can be divided into two. One subset satisfy this, another set not satisfied. So we can call it positive and negative. So when it comes to new data sets, we compare these data with the other. If there is exactly the same ones, then we can quickly use that decision, whatever we trained, right? If they are not exactly the same, then we need to see the closest ones and follow the closest ones. For example, but not necessarily, right? There are three different kinds of well-known techniques will be used. One, decision tree. Another, K nearest neighbor. And the other one is SVM. Okay, support vector machines. All of those are have been implemented and available for you to use. And a few of them are written in Python, a few of them are written in R. So we're going to use R, some tools in R. Okay? So, let's say this is new guys. Melissa, associate professor, years 7. So tenured no. What is this? This is testing data, right? So testing data, Tom, assistant professor, 2 years. This is a very good decision. And Georgie, professor, 5 years, yes, tenured. Joseph, assistant professor, 7 years, yes, tenured. But this guy is not tenured. So this is a decision based upon the classifier. That's what we are going to learn. So we can. So now you have a basic idea, basic concept of classification, right? I want you to consider the application in cybersecurity. Cybersecurity, particularly over the network. Let's say web services. The architecture is in this way. We have an internet, right? From that internet to our web server. Of course, we have a back-end database. We have a web server. And in between, we have a router and firewall. And router and firewall, usually we set up a rule, right? Some screening rule. So the rule can be installed and available and running. Therefore, you may have some decision data. So whether a certain request approved or denied, permitted or denied. So we have this decision rule. Once your classifier learns well, then when you have a real data coming in, then this real data is applied. And then this decision data can be constructed by some tools like SVM or KNN. KNN means K nearest neighbor. KNN or SVM, support vector machine, or decision tree. We call that C tree. Decision tree. C tree stands for a conditional inference tree. So based upon conditional probabilities, Bayesian theory has been developed, and that based upon Bayesian theory, a tree structure is constructed. Once it is constructed, using a decision tree is so efficient and fast. So which is good. But drawback of a decision tree is that once it is built, it's very hard to evolve, very hard to be adaptive to the world changes. Only to be adaptive is possible by reconstructing the decision tree, which is an expensive process, right? But anyway, if we have that, and also we can think of there may be some attacks. Although we set up rules that we planned, therefore we assume there may be no intrusion, but there is no such network infrastructure which never have succeeded attacks. So always attacks possible, right? So this slide shows that although we set up rule, therefore we have decision data, and that decision data is learned, is used to teach classifier. So classifier has some learning method, and when it comes to a real data, then we can treat the real data well, hopefully. But in reality, there may be some attacks succeeded. That attacks may be mutant attack, mutant, therefore not expected by rules. So rules never covers that mutant that is possible, right? That comes in my system. Another one is disguised attacks. Again, that disguised attacks may not be detected by the rules that we planned. Bypassed attacks. Some attacks not go through firewall, not go through the router, maybe some others, maybe internal. If you attack your system internally, you are already inside. So they're already bypassed, right? So all kinds of success stories available. How can we deal with it? We can deal with this. We can have rules to set up. We can have rules to set up so that we have a classifier. With this classifier, then we can train it and use it. So far, so good. But I want you to consider how you can deal with these guys. Okay? This may be only possible when we learn next module, which is a clustering. Unsupervised learning. Unsupervised learning. So for your group project proposal, if you don't do yet, then you may think of this. Okay? The idea is simple, right? It's a classification. You have a training data sets. So in the training data sets, you have a label. See here, label. That kind of packets, your label says yes, no, yes. Yes means permitted, no means denied. For example, your firewall rules determines one or the other. In real world, you have packets are coming in. Let's take a look at two packets. First package, well, we have similar ones. Then your decision is very quick. You can get something from here, right? Somewhere there. There may be another one. Unexpected data sets. These red ones. Then your decision is not really simple. If it is unexpected data sets, then there may be unexpected risk. You don't know the risk yet because you never imagined before. That is the real issue. That is the reason that we need to make our program more adaptive, eventually intelligent. And therefore, it can learn as it goes. Okay, first topic that we are going to look at is decision tree. Decision tree. Given data sets, this is a data set, right? This is a training data sets. In this, using the training data sets, we already built decision tree. Let's first consider the constructed decision tree. Once the decision tree is constructed in that way, then we can apply it quickly. When a new data comes in, right? New data comes in, then age is somewhere 35, and his income is low. Student will say no. Credit rating, medium, fair. Credit rating. Yeah. And we do not know this, whether this guy wants to buy PC or not. If some customer comes in, then we need to make decision by walking through this decision tree. So when you come here, and then this decision tree says, hey, you need to take a look at age first. So what is my age? It says 35. 35. If you take this path, only if age is less than 30. If you go to middle path, if your age is in between 31 and 40. If your age is over 40, then go to the right branch. So in this case, 35, right? 35 comes here, then it goes to this. So my decision is yes, quickly. If that decision tree is constructed well, then my decision is also yes. My decision can be made very quick, right? We just pass through that tree. Quickly. So that decision tree is based upon this kind of theory. There are some probabilities introduced on this slide. So prior probabilities, conditional probabilities, you may know this, right? Conditional probability. Given x2, what is the probability of x1? These are conditional probabilities. What do you mean by that conditional probabilities? So when you see here, students, this node, this particular node, students, is the case that when the age is less than 30, so there is a probability of some student information based upon age is less than or equal to 30. That is the case, right? Under this condition, we are now here to consider the probabilities. Student. That's conditional probabilities. So decision tree is based upon conditional probabilities. There may be some relationships. Okay, what is the probability of both x1 and x2? Okay, there is a joint probabilities. To solve joint probabilities, we need to consider whether it is dependent or independent. If there is a relationship, then these joint probabilities can be determined by conditional probabilities. So by taking one, and what is the probabilities? Second, vice versa. If they are independent, it doesn't matter. We simply, each probability can be multiplied. If they are independent. If they are independent, in this case, doesn't matter age or whatever comes, it is always there. Okay? That is here. Age, if we consider age in this range, it doesn't matter whether that's students or credit rating, high or low, it doesn't matter. As far as the age is in this range, then definitely he wants to buy PC, independent, but others are dependent. So Bayesian rule is this. So decision tree is based on Bayesian rule. Bayesian rule is based upon conditional probability. Okay, Bayesian. Who is Bayesian? There's a person. I don't know where the heritage of that mathematicians. His name is Bayes, right? Bayes. Bayes, maybe Bayes. So he developed that formula maybe centuries ago or millennium ago. So let's say if there is an evidence, okay, and there is a prior probabilities, and there is some likelihood, and therefore we can expect some posterior. Okay, this kind of a pattern is the concept that we build decision tree. Okay, so if you look at the decision tree, see here in this decision tree, we consider age first, right? And depending upon the value of age, we consider students. If the age in this range, the next value that we take into consideration is student's status. If age is in this range, then we don't care. We jump into the conclusion. If age is in this range, then we take another value into consideration. Credit rating. So the issue here is that which value needs to be considered and when. Are we going to consider age first? Or are we going to consider student first or credit rating first? When our target is to decide whether that customer will buy PC or not. What do you think? Which one is more dominant? The attributes: age, status of students, or credit rating. They are all neck and neck, right? We shouldn't do that without knowing a proof. How can we prove the first attribute that we need to consider is age? How do we prove next attribute that we need to consider when the age is smaller than 30? What is the rationale? What is the proof? Can we prove it? Can we prove it? So from the beginning, when we construct a decision tree, the most important question is that which attribute comes into the root along that tree structure? Which attribute should sit on top? Therefore, my tree structures will be more efficient. What is efficient tree structure? Efficient tree structure is this. You need to make a quick decision. If you need to take all possible attributes in order to get to a conclusion, then it's not be a good tree. By looking at one attribute without having to take other attributes into consideration, then that tree structure is the best tree structure, right? The worst data structures is that you need to take every single attributes into consideration in order to make a decision. in another community, in another application domain, the superiority of decision tree will be different. For example, database performance, so that you need to expect the computation time always equally the same in database. Database, that is very, very important, right? If some process takes 1 millisecond, but others maybe 10 days, then that is not good. That is not acceptable, right? It should be all similar processing time. That is one of the main purpose of operating databases. But decision tree, it's not like that. As far as we can make a quick decision, then we need to do that. If they all make a good decision, then that's good. Okay, so in order to verify it, we need to have some, looks complicated, but it is not really. So this is a good topic for your homework assignments, right? Some mathematics. The idea is this. This is the data. This is the training data sets. Okay. So for this training data sets, I want to build a decision tree. The concept that we consider here is information gain, by which attributes that we have higher gain. See here, if we take age, then gain is 0.2. If we take income first, gain is 0.02. So it's a 2% gain. In this case, 25%. If we take a student in first, then 15% gain. Credit card, then maybe 5%. So the best, the first attribute that we need to consider in order to construct a decision tree is age first, according to this computation. Then how can we get this number? So gain. So gain of age, gain of income, gain from students, gain from credit rating. How can you get it? The formula is this. Information gain, information value of entire data, entire table, which is this entire table, minus, let's say this table has information value, X information value. By taking this, you may lose some information. Therefore, what is the gain? Still, what is the remaining gain? Gain can be obtained by subtraction. So this is a given gain. This is by splitting. If we split, then we lose that much gain. Okay, so subtract that. Whatever the gain still holds, that is the value that we want to take as the first choice. So now we need to look at how can you get this info of D and info of D given age selection, given income selection, given student selection, given credit rating selection. So only we we make this difference, right? So information of D common to all the computation. So what is information of D? Information of D is the information of D is here. In information theory, the basic formula is this: negative probability log base 2 and probability. That is information theory. Okay? Negative probability times log base 2 probability. If you look at this, all that form, probability is 9 over 14, and the log base 2, 9 over 14. Same thing here, 5 over 14, log base 2, 5 over 14. Okay, that is the information theory. Okay, that is this. That is the information theory in this format. Let's say information, or target information right now, our target is whether buy or not. So looking at the computer, buy computed attribute here, by looking at this, we count number of yes and number of no. If we count the number of yes, then we have 9 yes and 5 no. For example, 1, 2, 3, 4, 5. 5 no's. So information is divided into 5 and 9. So 5 yes, no. 9 yes and 5 no's. What is the information gain? Information. So information is, what's the probability? Probability of class P, probability of class N. So class N we have 9, class N we have 5, class P we have 9. What is the entire size? 14, right? So 9 over 14, that is the class P. What is the class N? 5 over 14. So this is a probability. And this is a probability of class P. So actually it is a negative P log base 2P. Same thing, this. 9 over 14 and probability log base 2, 9 over 14. If you compute that, for example, if you compute it, bring it, okay, here. How can you use? I don't have my mouse. Okay. Here, okay. So, let's say 5 over 14. 5 divided by 14. There's no equal sign. Okay, equals. And then we need to apply that to log. This log is not, I'm not sure this, what is the base. But doesn't matter. It's 5 over 14, then it's less than 1. Therefore, the value is negative. Right? Value is negative. Negative 0.4. This is negative. P is less than 1. Therefore, we have negative up front. So entire value here, information gain, is positive, becomes positive. 0.4 from this log, but we applied that to 5/14, so 30% of this, so maybe 0.1 whatever, right? That is for this second term. First term is very similar to that. So entire information gain based upon this attribute of this table is 0.9. So this is 0.9, 0.9. What's the information gain based upon age? Okay, age. Then we need to take the age column into consideration, this age, right? That is nothing but this. If you consider age, we count less than 30 according to this value, right? In this range and that range. We count positive and negative. Less than 30. This guy, no. This guy, no. Less than 30. Less than 30. This guy, no. Less than 30. This guy, yes. So not all, no. This guy, also yes. So 2 of them, yes. 3 of them, no. We count all of those. In this range of age, how many of them eventually buy or not buy? In this range, all buy. No, not buy. In this range, 3 of them buy, 2 of them not buy. Okay? So we compute this I of P, I, and I, and I for each case of this. This and I information is nothing but this. We already counted, right? So this can be computed here, which is I of positive 2 and negative 3. So 2 comma 3. I over 2 comma 3 is nothing but here, this information theory, right? Negative P. What is the probability? 2 out of 5. So 2 out of 5. 5 means we add those 2, right? So entire value is 5. We add them. And then 2. That we consider. So log base to 2 out of 5. Plus negative 3 out of 5. So 3 out of 5 and log 3 out of 5. So we need to compute this. Then we will know what it is, right? So this is some value. This value goes into this. Similarly, another value here. See, if you have 0, then 1, 0, and the other 1. So anyway, that is 0. In this case, I think that is 0. 3 comma 2, that is the same as this. We use double, right? By computing this, we use that. We can feed it into 3 comma 2 and 2 comma 3. They are the same, right? Total 5, and therefore. So I explained here what do you mean by this? There. Okay? You can interpret that all around. So by having that computation, we say that, oh, age will appear at the top first. Once it is appear at the top, how can you make the rest. Once it is appeared, then we consider only the case here. The next time that my entire database will be the database of this, and this, and this. So by taking only 5 rows to be an entire database, that database is this database, this entire. See, this entire database, that database will be this entire database. And then redo all of this to find out which one's best. So that is next time the best attribute may be students rather than credit rating. We consider only two in that case. A little bit of a hassle, but not impossible, right? So in that way, you may have optimal decision tree. So using decision tree is very simple, but construction, it needs some work. So beauty of decision tree is that it's quick and easy to use once constructed. But only problem is construction. Number one. Number two problem is it's not really flexible to adapt to the changing of the world. But anyway, this is a decision tree. Okay? It's all. So we can use some tool to build. There are some tools available. They are written in Python. Tools available in R, but we are going to use R. Okay. So that is a decision tree. Any question about decision tree? We'll do hands-on the next week. When I use hands-on, if we have a very, very, very few rows, say that example, how many rows? We have 14, right? If you apply that 14 rows, because it is so small sizes, you cannot have a critical the information gained to construct according to that R tool. It doesn't produce decision tree well. But if you increase the size of the database, you can make a good decision tree. So we'll practice that.
So is there a minimum size for the data?
Yeah, I think so. There's some implementation issue. But I try to find out. It depends. There are a lot of tools available, by the way. Okay? So best way is that if you implement this in Python using all the information gained, you may have a better decision tree tool rather than using tools. But in R, we simply use it. But if you work on Python, then you may build your decision tree more efficiently. That's what I am feeling. But I'm not interested in making a decision tree. Alright. K-nearest algorithm. This is something that I like, and many also. This is a more programmatic. The example is the same example that I gave it to you from the beginning of today's lecture. You have neighbors, so you know the good neighbors and bad neighbors in your town. And when a new neighbor moves in your town, then you may want to make decision to find out your newcomer tendency, maybe good neighbor or bad neighbor, right? How do you make that decision? We need to calculate the distance. Okay. The distance function. There are very different distance functions available. If you implement this k-nearest algorithm-based classification in Python, then you can do a lot of on your own manipulation. You can use different distance functions and all. So you may have a lot more dynamic k-nearest neighbor function-based classification. But rather we will be in simple way. Okay? Simply use R. So we're going to use a specific tool. So it classifies well, but not much that we can be involved in because it's not a program. So distance function and select k-nearest examples and count how many. And then we will take the most common. Let's say I make a distance. We have here. How many people? 2, 4, 6, 8, 9, including me, right? Say I'm new. Okay, you are the testing data sets. So 8 objects are in the testing data. So so among you, because this is a supervised learning, we have labeled. What labels is good? Republican and Democratic? I do not know, right? I'm not going to ask you, but the Republican and Democratic. Then there's a bisect, right? Bisect. So maybe half of you Republican and half of you Democrat. I'm here, okay? I have no tendency right now, but I'm going to follow. If you have very similar to me, then I'm going to be labeled either Republican or Democrat. Each object from testing data sets, you have some features, right? Say age, education level, what else? Race, marriage status, income, number of credit cards, whatever, right? So I do have the same values. So I want to compare me and each one of you. Me and each one of you. if let's say if we consider 5 features, which means 5 attributes, 5 columns in the table, okay? 5 columns. How do you compare? So that how can you make distance functions? Somewhere I made here distance functions, right? Where is it? Yeah, this is distance functions. In this case, we took only 2 dimension, right? If we have 5, then we have more. More of this square plus more of that square. If we consider 5 features, we do 5. I can compare, say, your income and my income, subtract and do that. And age we also subtract. And what else? There are many, right? Number of children. 2, 0, 1, whatever. James has no children, right? No child. Jess, George?
No, no,
No, right?
no.
I'm not asking you married, but
No.
without marriage, somebody has a child. Just kidding. Oh, Peter, you married?
Yes.
Oh, okay. Anybody have a child with no marriage? Okay. All right. So we can make some distance, right? So I have let's say me and Anno, we have distance 5, and me and Fred I have distance 6, and me and Shake I have distance 4, and something like that. We have some distances. So I rank the distance. Okay. From shortest distance to the longest distance. K nearest neighbor means, am I going to top 3, top 4, or top 5? That means K nearest. Here, so we calculate distance, right? And then K nearest example. K nearest. Say 3 nearest. Then top 3. Top 3. We choose top 3. So I have some top 3, say with the Shake and Peter and Fred. Those 3 are top, shortest to me. Okay. Then what should I do? I need to ask their label. So one guy said Democratic, the other guy said Republicans. Whatever. Among those top, whatever K is, I can follow that group, right? The majority of that. Majority label of that top K matches. Then I'm going to follow. That is a K nearest neighbor algorithm. Do you understand? So algorithm is very, very straightforward, right? Very, very straightforward. You can apply that algorithm in many other cases. Maybe military use that algorithms a lot. Military has some specialties, and therefore they have some assignments, right? So, you go to this company, you go to that company, because you have this skill or that skill. And when you enlistment comes, then according to that K nearest algorithm, they can assign. That assignment is optimistic. Because they already have some label. Their label, the training data sets keep updating. Okay, in military they have, by assigning this guy to some company, we have so many bad stories than the bad label, right? By assigning this guy to another company, oh, he maximized his capabilities and he made a big contribution. There's a big positive, right? So having those positive and negative training sets, training data sets, if we have that, then when new guy come in, then we apply that rule. Apply that rule is very, very simple. It's not like, we first find out some rules and describe that rule and apply that rule to an example. It's not like that. K-nearest algorithm is that we still stay with the data sets. We don't describe any rule. We still have training data sets. We have testing data sets. If we update training data sets, our decision will change. So this is totally based upon data, right? Data. Data, as far as data reflects the real situation, our learning process is always based on the current situation. Okay? That is the beauty of K-nearest algorithm. K-nearest neighbor algorithm. Any comments? So are you excited to use it? Why? Decision tree is so simple. Only there is some drawback, which is the construction. If that construction is based upon information gain, right? Information gain. But if you do programming, then that computation is also simple, right? But computation is by paper and pencil. Oh yeah, then that is too much work.
Yeah, if everything's up to the computer, I'm sure it's all the same. But yeah, if we're trying to actually figure out stuff out, computers,
So you want the homework assignment from K-nearest neighbor algorithm? Still, that is based upon paper pencil. Look at this. This is a distance function, and okay, this example. So we select 3. In this K nearest neighbor, let's choose 3, number 3. So I want to choose top 3 matches, and then I'll follow the majority. Yeah. And this is my targets. Response yes or no. Okay, only binary. This is a new guy. This is new. Oops, this is new. All others training. Training data set. Training data sets. So we have labels. So the features of each object here is from here there, right? Only 4 features to be considered. Customer name, age, income, number of credit cards. And the label is responsive.
yes. Would it be John Rachel's closest neighbor?
Oh, you're talking about, asking about this David?
Yeah. Who's
David is new guys.
Yeah.
Yeah, up to this is training data sets, which means we already had good record of that. So we train our classifier with that training data sets. And then the last item comes in. Then we can make decision. What would be his response? Yes or no? Oh yeah? I didn't know. So we look at, we compare, we calculate the distance, this guy, and this guy, and this guy, this guy, right? We compute the distance. How do you compute? See, this is a square root of each subtraction and power 2 in this. So we compute that. The distance, these two guys is so high. The nearest, top nearest 3 is this and that, right? So 15.16, 15, and 15.74. So we look at that. This guy says yes. This guy says yes. This guy says no. What is the majority? Majority yes. So yes, yes. Right? Because then this is.
Well, I mean, I was correct if you're working on that.
So how did you get the yes? Tell me.
I just compared each category. So, first, like, there's like non-responses, because you didn't know who responds. I looked at number of cards, I looked at the income, and then I looked at the age tracker, and then which was like, general similarities in other people. So I mean, it was John Richard.
So actually what you reason about is if we formalize it, then it is based upon that distance function, right?
Yeah.
So what you have been thinking and reasoning about is informal, but if you make it formal, then that is based upon that distance function, and we choose k nearest neighbor. If k is 3, then top 3. If k is 5, then top 5. Whatever, k. And then we follow the majority of their label. Okay? So he didn't, what he didn't do that here, he didn't follow this label and that label because theirs is much different from me. Right?
Yeah.
So, if you want to make sure, using k-nearest algorithm, then you can say, okay, my decision is based upon k nearest neighbor, but my confirmation is that k longest neighbor, okay, top 3 matches, and then bottom 3 matches. That bottom 3 matches help me confirm. Confirmation is that, hey, because of that, my answer is definitely yes. It is not no, right? It is not no. So basically, what JP says is that, because that is not no, his answer is yes. Okay, that is his confirmation. But his original, the forward reasoning is that based upon that. Okay.
I just feel like if we use the same data, we could draw different conclusions, just depending on what we're searching for, right?
Oh yeah, what actually, right?
Yeah,
Sometimes
exactly.
we use 3 of those, right? Not only that, probably you may raise this issue. It is not normalized. Number of difference income. In this case, we treat all the values as is, right? We didn't normalize the values. For example, number of cars is not more than 10. right? Usually. Maybe 1 or 2 or 3. But age difference is usually bigger than 3, or right? Age difference is not more than 100. But income difference is definitely 100 or 10,000. So, but here in this computation, we treat the value as is, which is not good, right? We need to normalize. How can you normalize it? We need to entire sets. Age, for example, maximum 100, minimum 0. Then we need to compare that, whatever the value difference, over 100. Income, say, 10,000 difference, $10,000 difference. What is the income range? Maybe 10,000 to 100,000. Okay? Then 10,000 over 100. So maximum value needs to be in that denominator of that fraction. So we need to make that all in fraction. That is normalization. Same thing, a card, credit card, number of credit cards. How many credit cards that we might have? Credit card companies, major credit card companies. Not more than 10, right? Let's say 5. So difference of those, that over 5, we apply denominator. So magnitude of that difference is more like normalized. Therefore, difference of income may not be dominant on that computation, right? Right now, income difference may, even though they are all the same, for example, David and let's say James. James comes. James' age is 63. He has credit card 1, but his income is 50. What would be his response? But I do not know, but because this is a big difference, right? So this may dominantly change it. Therefore, his answer may be, again, yes, because this is a big difference, right? But if we consider this, his age, this guy is 63, is 59, all the people says no, right? If we consider this, then there's a big difference. If you consider this, they are the same. If you consider this, number of credit card 1, they're all the same also. So except the income, the other two attributes are exactly the same. So real answer may be no, right? But if we apply that to the value as is difference, then definitely that is. So that computation needs to be normalized. Okay. The tools that we are going to use, as I said, there are many tools developed, so we will use one of those. Idea remains the same, whichever that you want to use. But implementation, most of them are calculating normalized distance function, but if you choose carelessly non-normalized distance function, then you may have wrong decision, right? So be careful. So one nearest, if we have this, one nearest neighbor, we choose only one, top one. I'm going to follow top matches. That is one nearest neighbor algorithm. Three nearest neighbor algorithm. Is this, right? If you have so many distance, are we going to compute all of this distance, that and all the way that and all the way here? If we have 1 million data sets, then our computation is 1 million times. Are we going to do that? Or are we ready to make a some representative, maybe average, median? If that is not placed in real object, then we choose a real object instead of that virtual. There are a lot of issues available, right? So we can simply compare this and that and that. There are many different ways. There's a KNN algorithm. If we have this, then someone may want, hey, I want to divide it in this way. So quickly, okay. That is a support vector machine. Support vector machine. But I'm going to stop here. We do not have enough time to cover support vector machine. I'm going to give you a lecture, my video. But support vector machines theory is, it has a very, very long theory available. But we're not going to cover that all. But I'm going to give you just broad concept of support vector machine and simply use the K and the tools. Okay. So using tools will be on your video lecture. Okay. So next week there's no physical.